Okay, this is a continuation of that previous video. Okay, so we're working on Atwood's machine over here. We ended up with the first mass getting a formula for the free body diagram for that one. And the second mass, we ended up with this formula here. We solve for t here, and we plug it into this t of the second formula. Okay, and then we end up getting these two things here. This is your t, m1a plus m1g, and then minus m2g comes from this formula here is equal to minus m2a. And so I just plugged in this t into here to get the following things. Okay. Now, I regrouped all the a terms to one side and all the g terms to the other side. That's basically this next line here. Okay. And from here, I basically factor out an a and a g, like so. Okay, and I divide both sides by m1 plus m2. Okay, and so you end up with a is equal to m1 plus m2. I'm sorry, my bad. M2 minus m1 parentheses times g divided by m1 plus m2. So you end up with this formula here for the acceleration. Okay, now what does this mean for the Atwood's machine? Okay, up here. So the acceleration, which is given by this, if m2 is equal to 0, okay, if m2 is equal to 0 here, then you end up with minus m1 divided by m1 times g, or negative g. So basically, if that's the case, then this thing goes away, this thing will drop downwards this way, with the acceleration facing the opposite direction. So it's going to be moving downwards in free fall. Okay? Same thing happens when you plug in m1 is equal to 0. Okay? Now, if m2 is equal to m1, look at what happens. m2 minus m1 will give you 0. And so the acceleration is 0 for the system. In other words, if the two masses were identical, then what ends up happening is this thing will be either at rest or moving with constant velocity, which is basically what you would get in reality for something like this. Okay, so that's Atwood's machine. Okay, let me go ahead and erase this now. We can move on to bigger and brighter things here. All right, for those of you who are just looking at this video is probably not seeing much sense in what I'm talking about, I refer you to the first video. We go through a number of different scenarios, from simple problems in forces to more complicated ones. Okay, now here's one that we run in lab. Okay, this is frictionless surface. Here we have m1 on the frictionless surface, and then we have m2 over here. Okay, so this is kind of like the Atwood's machine, except that you don't have these things hanging downwards, both of the masses hanging downwards on a pulley. This pulley is, again, massless and frictionless, and it's supposed to be round, but I'm getting tired. So anyways, let's take a look at what the free body diagrams are going to be for this one. Okay, now intuition indicates that this thing will accelerate. Okay, in this case here, it'll move this way, and for m2 it'll move downwards. Okay, so we draw a free body diagram for these things. Let's start with m1. So we do this, and we take a look at the forces on this thing. Now for this one, the normal force and mg are pretty much going to be equal and opposite to each other. So n is equal to mg, as we've seen in previous examples, so I won't write that one up. The one that is of interest to us is the one that is causing the motion this way. Okay, this is tension along that string. Okay, and so if we do the forces along the x direction, we end up with an acceleration. This is going to equal ma. Okay, so all the forces along the x direction is just t. Okay, so t is equal to, t is equal to, m1a, because there's no other forces on this thing along the x direction. All right, the indication of acceleration is this way for this one. Okay, so T is equal to M1A is what we get here for that one. That's it. Okay, now we put a box around that for the moment, and we move on to the other mass, M2, this one here. Okay, now for M2, we have a tension upwards, and we have M2G, which is the weight downwards. And we indicated that the acceleration is downwards for this one. Okay, so we add up the forces again. Add up the forces in this case along the y direction, because it's vertical. Okay, along the y direction we have T upwards, and then an M2G downwards. So we put a minus sign in front of it. This is equal to MA. In this case, it's M2. Okay, and because the acceleration is downwards, we put a minus sign here. All right. Now, we put a square or a box around this one. That's all we can do with that one on its own, but we notice that T up here has already been given a value of M1 times A. So we plug that into here, we end up with M1A minus M2G is equal to minus M2A. All right, regrouping everything, we end up with M1A plus M2A is equal to M2G. And then, minus M2G. All right. Sorry. What did I do? Oh, no, this M2G. This is plus M2G. Sorry. I'm getting tired. So minus M2G becomes positive M2G when I move it over. Yeah, so that's correct. Okay. A, M1 plus M2. So I'm regrouping that, factoring out the A. This is equal to M2G. Then we divide both sides by M1 plus M2. We end up with A is equal to M2G divided by M1 plus M2. Okay? And so there's your acceleration for this one. Again, you can test this out. If M2 is equal to 0, then the acceleration is 0. And that makes perfect sense for this thing, because if this is 0, then this thing will not accelerate. Okay? If M1 is equal to 0 according to this formula, okay, then you end up with M2 divided by M2, okay, times G. And so you end up with A is equal to G. That makes perfect sense too, because if M1 is equal to 0, this thing's just going to move downwards in free fall. Okay? So that's that one. And again, for any of these problems, we get to the point where we get the acceleration formula there. That's not the end, actually. Okay? And if you are given additional parameters like time, how long it takes to move from rest or from an initial velocity, then you can actually work your way through with this acceleration value, figure out what the velocity is going to be at a certain time or the position at a certain time and so on. Okay, and so this is just a beginning. This part here, up to this point is all dynamics, basically trying to figure out what the forces will indicate. Okay, after which, once you get the acceleration, then you can plug that acceleration in to get the velocity and the position and all that other stuff. Okay, the stuff you learned in earlier chapters. Now, let's try this one. This one seems a bit more complicated. Okay, it looks kind of like a combination of a bunch of the other ones that we did. Okay, but it's no different in terms of the process. Okay, we are using the same processes that we've talked about before. Drawing a setup diagram, which we just did. Draw a free body diagram. We will do so, and then we apply Newton's laws, okay, as needed for this thing. Okay, so here we have two objects with mass, so we'll go ahead and use those two for the free body diagrams. Okay, starting with M2, just to make sure, because it's fairly simple. Again, we indicate direction of acceleration. Now, if it turns out that M1 is bigger than M2 and it's causing the thing to roll down the other way, then so be it. What ends up happening is your acceleration will have a negative value to it. Okay, and that just means your assumption of direction is incorrect. It's going the other way. Okay, but for the moment, let's just assume this for the time being, that it's going to go in this direction, and we'll see what happens. So for M2, we draw the tension upwards, and we draw M2G downwards. And again, the acceleration is downwards in this case. And so it's very similar to what we had before. The sum of the forces in this case is going to equal MA, okay? But in this case, we have t minus m2g. This is equal to ma, okay? But a is negative, so we put a minus sign there, okay? And it's m2, so we put an m2 there. And so there's the formula for that one, okay? Now, come back to this thing here, take a look at this and draw the free body diagram for the M1. So we do this, okay? Now, we have this thing at an incline, and as I mentioned in the previous video, this is going to result in an M1G downwards this way, where this angle here is theta. If you don't remember how to get theta there, you'll have to go back to the previous video and take a look, okay? Now, from here, we have some other forces involved in here. We have the normal force going this way, okay? And we have the tension on M1 going this way, all right? But now what we have to do is break up M1G along the coordinates, okay? And so M1G is going to have a sine and cosine component to the thing. So I'll draw this here. One going this way, one going this way, and they're in blue just to indicate that these are the components, okay? So here is the adjacent side, so this is going to be M1G cosine theta. And this one here is going to be M1G sine theta. Okay, again, this is right angles here. Okay, now, also indicating acceleration, it's going that way. So we write down the free body diagram, the forces for the free body diagram. Along the y direction we have, use the black pen again, some of the forces along the y direction, it's going to equal n minus m1g cosine theta. Okay? m1g cosine theta, yeah. And this is equal to 0 because there's no acceleration along that direction. And that indicates the following. N is equal to m1g cosine theta. Okay? No big deal there. We don't have to worry about that so much. Not in this case, at least. Okay? Now, in the x direction, we have t. Oops, let me write this down. Sum of force in the x direction is going to be t along the positive x direction. I'll write down this as capital T. Okay? T, and then a minus m1g sine theta. Okay? And those are the only two forces along that direction, along that coordinate. Okay? In this case, it has to equal ma. Okay? And in this case, it's ma, but the mass is m1, and the direction is positive x, so we don't put a minus sign in front of it this time. Okay? So we end up with this formula here for the second object. Okay? So we have t minus m2g is equal to minus m2a, and we also have t minus m1g is equal to m1a. All right? Again, you have two equations and two unknowns. So you have the normal force one, but we'll sort of forego that one for the moment. Okay? What I'll do is solve the first one here for t. So this becomes t is equal to minus m2a plus m2g. Taking that, plugging it into this t here, okay, we end up with minus m2a plus m2g minus m1g sine theta is equal to m1a. Okay, so far? Now, we regroup all the a terms to one side. This is m1a. Okay, regroup all the a terms to one side. We get the following. We'll put them all on the right-hand side. m1a plus m2a. And then we end up on the left-hand side with all the g terms. Okay, we get m2g minus m1g sine theta. Okay, so we end up with that. So m1 plus m2 times a on the right-hand side. Left-hand side, we can pull out a g. So we end up with m2 minus m1 sine theta over here. We divide both sides by m1 plus m2. The acceleration is going to equal m2 minus m1 sine theta divided by m1 plus m2 multiplied by g. Okay? And there's your formula. Okay? Sorry for the jittery thing. My arm's getting tired. But you get an idea that, with any of these things, you follow the same steps. Okay? It'll give you the means to solve these problems. Okay? To get the acceleration for these free body diagrams. Okay? It does take some calculations and some, scratching of your own head to figure out these things. But with a little bit of practice and reviewing this video along with the previous video, hopefully that'll give you enough information to understand the steps on how these sorts of things are solved. You can also work on other types of problems if you wanted to. For example, if you have 3 masses, something like this, okay, where you have 3 masses, and this is a frictionless surface with 2 pulleys, one here and one over here. This is M1, this is M2, and this is M3. You can solve this, okay? What you're going to have to do, though, is solve the free body diagram for this one by itself, this one by itself, and then this one by itself. And since there's 2 strings here, you're going to get T1 and T2, 2 separate tensions, okay? So this mass here will have a tension upwards of T1. This will have a tension T1 going this way. This will have a T2 going this way. And this will have a T2 going upwards. Okay? Along with the mg's for each one of these things here for their appropriate masses. And you'll get 3 equations basically for this one. All right? Actually 4 if you incorporate the normal force and the weight for the second mass. Okay? But the idea is that using those formulas, you can actually solve for the acceleration of the system. You have to assume the direction, of course. Let's just assume that this is going this way. Again, if it's incorrect, it'll show up as a minus sign in the formula. Okay? But you can solve that kind of problem now using the same sort of steps that we did here. Okay? Another example would be something like this, where you have an incline, a mass, a pulley, and then another incline over here with a different mass. And these angles here don't necessarily have to be the same. They could be different values for these angles. This could be theta 2. This could be theta 1. You can solve this. Okay? It's just a matter of working through the free body diagram for this one and the free body diagram for this one. Again, assuming the pulley here in the middle is massless, okay, and frictionless. And assuming that these surfaces are frictionless as well, you can solve this problem. All right? Now, if these do involve friction, it's just a matter of popping in an additional vector that opposes the motion. Okay? Now, for that one, I may have another video for that one sometime in the near future, but for the moment, I'm going to forego that because I'm out of time and my hands hurt. Okay? I'm tired. Okay? So hopefully that will is enough to help you along the way here with these types of problems. Okay? Good luck with these free body diagrams. This is Mike Masuda.